very easy and also the most difficult thing in the world at the same time. In the early goings, it's entirely dependent on your knowledge of derivatives. Because if I were to ask you what is the antiderivative of cosine, if you know all your derivative rules, then you can immediately tell me sine, right? So there's a little bit more to it than that, but that's essentially the basis of it, right? But moving forward, you're going to be faced with situations where you're looking at a function that's not recognizable as the derivative of some other function, where you have to manipulate it in some way. All right, we're not there yet. We'll get there. That's what the other 80 some odd pages are for. But at this point, we're really just focusing on working backwards based on the wealth of knowledge that you have from the first semester.
So the whole second semester is antiderivatives?
Yeah.
Right. Let's get this.
And the application of those. So I'm just gonna off on the side here sketch out something for you. You don't have to do this because you already have something along these lines from what we're talking about with linearization. And this is really the reason why I don't feel too bad about introducing this topic prior to assessing on linearization and Newton's method and differentials. If I have some arbitrary function, as you know, it's the same arbitrary function every single time, and I'll give it an axis, and you have some point on that function. I actually touched on this when we talked about derivatives, very early going. There's a couple of things that we could do with this point. We could find the slope of it. We could find the slope specifically at that point. We could find the slope on an interval, so starting at that point and terminating at some other point. But another thing that we could actually do is find the area beneath that point. You think, well, how can I find the area beneath a single point? If it's a single dimensional point, how does it contain any area? Well, if I were to draw a line downward, we would have some vertical distance that we would call y. All right. Now, still doesn't contain any area. But if I just kind of shoot over and create a rectangle, that single rectangle would have some area. But then you would say, well, you're moving away from the point, so you just kind of defeated your own argument. Well, if I tell you that little distance, that little movement is dx, then what I'm saying is it's an infinitesimal movement, right? So when we talk about dy dx, for example, instead of delta y over delta x, so change of y over change in x is that over an interval. Dy dx is at a particular point. Slope of the line tangent to a curve at a single point represents instantaneous change. Right? So what's happening is you're taking those 2 points that are separate from one another and moving them towards one another and determining what the slope would be if they were ever to get to the same location based on the trend that develops numerically. All right? That's the same idea here. You would have some rectangle with a discernible width. We would be decreasing that width till we get to a point where the 2 lines are indistinguishable from one another. Right? If that ever happens, then the width between those 2 vertical lines would be dx, right? Some instantaneous change. But what we get, most importantly, out of this is an area. Area of this rectangle would be y times dx. All right, y times dx. Now, what is the y times dx going to give you? It's going to give you an area, but if I can make a determination, and really if you think about it, it's like this little sliver of area, how useful could that be? Well, if I tell you that this interval starts here at some point A, and then terminates over here at some point B, what I would want to do is collect every possible area for any possible rectangle on that interval, right? So what I would be looking to do is find every single possible area and integrate them all together, right? So collect them all and combine them together. So how do I do that? Well, I use this fun symbol, which is a symbol for an antiderivative, but it also means integral, right? It's a command to integrate. There's a summation technique that we're going to learn down the line that actually justifies where this symbol comes from. But really at this point, all it means is the collection of all possible areas for that arbitrary rectangle over the given interval. And as a result, I would be able to determine the area from A to B, right, under any curve, right, as long as it's a function. And then later on, you know, later in this course and then in future courses, you could see that this would work for any function. Right? So what we get here is that this is known as a definite integral. Right? The symbol, like I said, integral also means antiderivative. Right? So in order to be able to handle a problem like this, we would have to know how to find antiderivatives. Right? The benefit of knowing something like this, well, I would say it's obvious, but it's obvious only if you care, I guess. Right? What that would mean would be like you care about figures other than your standard geometrical figures, like a circle or a square or a rectangle or something like that. So if you don't care about what the area would be for, you know, under a curve like this, then you know you'd never even think to do something along these lines. But if you do, then this is where this comes into play. The Waze app. I just saw it. It was really cool. The police are half a mile ahead app? Yeah.
That's the only reason why I like it.
Put it on every morning, just for that. Let me see.
Yes. But sometimes I like to get places faster.
So, what an integral will do is actually help you collect areas, like I was saying, for arbitrary rectangles. But it's actually accumulating those areas. All right. So as you increase in time, depending on what the function is related to, you can, assuming you're talking about time, you're accumulating each one of these measures, whatever it happens to be representing. If you're talking about density associated with traffic, then it might be important to have a full collection over time. So I found an example, a real life example of integration involving these rectangles. So if you go to your Waze app, you put in your destination and then you select find the best time to leave, view more times. You know, you could put in what time that you want to arrive. Then off on the side there, you see the little graph of traffic. If you turn that on its side, well, turn your head on its side, I guess. What you're looking at is a real-life example of the integration of infinitely many rectangles. All right, because each one of those rectangles represents a density at a particular moment in time. All right, collect them all together, and you would have an overall sense of the density of traffic throughout the day. All right, so real-life example, pretty cool stuff. All right.
Thank you, Reese.
Just so you know, 5 column gets considerably bigger after 4:15.
It's called rush hour.
Wow.
But if you have a function to represent that, then you can mathematically make a determination of when traffic would be at its most dense. So, I mean, if you have no choice, I mean, you look at it, I mean, best you get from that is, I'll stay away from that area at that particular time. But, you know, like, is there an optimal time at which you would be? You know,
Friday's
that's...
rush hour is earlier than the
Really?
Because people try to get home a little earlier on Friday.
Right. But then I've also gone the route of, like, okay, so my extended family lives in the DC area. So I know you got to deal with rush hour traffic on both ends potentially.
So bad.
Yeah.
The worst.
So, like, I'll say, all right, I'm going to leave here after, let's say, 10 a.m. to avoid rush hour traffic in this area. But if I do that, I run the risk of squarely hitting all their rush hour traffic in the afternoon. You know, so, I mean, it is a simple matter of addition and subtraction, but, you know, there is some calculus behind it.
Usually when you leave for something, you have to be there at a certain time anyways.
Right, that, yeah, you have some constraints that make
just, like,
calculus unnecessary, but there is a thought behind it.
Route 35 is busiest between like 4:15 and 7, but also between 9:30 and 10. Just so everyone knows.
9:30 a.m.
Just to get to Maryland
Oh,
for
p.m.
hours.
Yeah.
Huh,
I find out
That's weird. That's not, that's
that's weird. I wonder why.
Hey, I'm just telling you the ways that
Like, what's the budget? Like,
So I will be developing a project based on the Waze app just because I'm inspired now, so I'll figure that out.
project.
Yeah, project. I've just got to, I just verbally committed to that, which was stupid. I should have kept my mouth shut. But I will try to do it. So anyway, very simple example of an antiderivative. X squared is the antiderivative of 2x. Actually, x squared is an antiderivative of 2x because there could be some constant c added to x squared that would allow it to be also an antiderivative of 2x. So let's say I had x squared plus 2. If I take the derivative, I get 2x. X squared minus 10. Derivative 2x, and so on. So infinitely many possible antiderivatives of a particular function. Right? So something to keep in mind. The notation, very straightforward, I think, because we covered differentials. The differential form is what you would get if you were to take the derivative of a function and then just multiply both sides by the dx. All right, that's the differential form. Any equation that is in the form involving a dy dx, it doesn't necessarily have to have dy over dx, is known as a differential equation. All right. When you put it in differential form, you make it easier to anti-differentiate. All right. Anti-differentiate is the same as antiderivative or integrate. All right. So the terminology is kind of all over the place, but it all essentially means the same thing. Just like in the first semester, just about everything meant find the derivative. Now just about everything is going to mean find the antiderivative.
So the differential equation is an equation that just doesn't have a constant.
It does not. Well, it could have a constant. It's the constant was the result of some linear function when you took its derivative. Right. So just follow the progression on the notation, and you can kind of see how this plays out. dy dx equals f of x. In differential form, dy equals f of x dx. But if I want to solve for y in terms of x, that is not the scrolling tool, which is my finger. I would take the antiderivative of lowercase f of x dx. The notation-wise, lowercase f of x has an antiderivative of uppercase f of x. So just to give you a sense of the hierarchy here, we're looking at the any given function. Sorry, it gave me an error message. Function f of x. You have the first derivative. It's spazzing out on my iPad. First derivative would be f prime of x. Then you go to f double prime and so on. But then going backwards, you would have the antiderivative. Let's go purple for those keeping score at home. The notation is capital F of x. We don't say things like the second antiderivative. You can take the antiderivative of an antiderivative. The issue is every time you take the antiderivative, you're going to introduce a constant c. Generally, before you take an antiderivative again, you would want to flesh out what that constant c is, right? Particularly. Right? So generally, it can be anything, but usually are some constraints or some conditions that are given that give you a sense of what that C value truly is, right? So you'd want to flesh out what that is before you go ahead and take the antiderivative a second time, right? So just to give you a little sense of the notation. So it's not like you make the F bigger to anti-differentiate again. It's just, it doesn't work that way. All right. This little table here is really just us remembering what our derivative rules are, and just kind of working off of that. So we would want to be thinking, what kind of function has a derivative equal to 0? C, some constant C. All right. K represents some other kind of constant. It's kind of weird because not all constants are created equally. You have constant of integration, but then you have constants of whatever.
Kx?
Yeah, it's going to be Kx plus C. Right? So this K might be like a constant of proportionality. It might be a constant in a scientific context, like a coefficient of static friction. Is that a thing? Did I use the term right? Okay, cool. Yeah, I mean, I don't know anything beyond the name, but oh, it would be mu. Okay, so it would be a different type of. It wouldn't be K, but it would be some kind of constant. But it would still. I know exponential growth has a K in it. Spring constant. Yeah, there you go. So we have a variety of possible constants.
Also, it's 9.
What's that?
K is the Coulomb's law constant, 9e9.
9e9.
No, that's the physics reference. Yes, it's 4 years ago.
But it's also a lot of other things, though. So like.
Yeah. It's not just limited to the one thing. Yeah, we can't just pin it down. K is very malleable. K lowercase f of x. You could rewrite it because the constant multiple rule for derivatives and limits and everything, well, there's also a constant multiple rule for antiderivatives. So ignore the constant, anti-differentiate everything else, and then bring the constant back in. What's the antiderivative of lowercase f of x? Uppercase f of x. So K capital F of x plus C. All right, x to the nth, that's a power function. Right? We have a power rule that tells us to take the power, multiply it by the coefficient, and reduce the exponent by 1. So let's just do the opposite of that. Increase the exponent by 1. And then divide by the new exponent. Numerically, it seems to make more sense, though. Because you look at this, it's like, oh, that's unnecessarily complicated. But if I had x to the third power, say y equals x to the third, and I want the derivative, not the antiderivative, but the derivative, I would take the power, multiply it by the coefficient, it would become 3 times x to the second power. All right, so if I want to go the other way, so this is actually a good way to get a sense of how to do this from beginning to end. I'm given a differential equation. I would put it in differential form. Then I would integrate both sides because integration is an operation. And if you operate on one side of an equation, you have to do it on the other side also. All right? So here I would be doing the exact opposite. So I would increase the exponent by 1 and then divide by the new exponent. All right? So 3 divided by 3 would be equal to 1 plus C. The antiderivative of dy. Now, the notes would have you believe that dy just becomes, or magically becomes, a y. But if we assume that there's a coefficient here, an understood coefficient of 1, it really would be asking, what is the antiderivative of 1? Yeah, it's going to be y, right? All right. So then it would be an important thing to talk about at least once. If I had to add a plus c over here, shouldn't I also add a plus c over here? Probably, right? Are these two c's equal to one another?
Yes.
Yeah.
Perhaps. That's a key. Uncertain. Right? We don't know. All right. So I can't make the assumption that they are.
Based on that, wouldn't it be 1/3 x?
Right, but since there was a coefficient of 3,
Yeah.
I'm going to divide, or it'll be 1/3 multiplied by the 3. Which
So
is
why
going to
isn't
cancel
that
that.
in the equation?
Because that one didn't have a 3 coefficient to begin with. So this one would really be, the 3 was there. We would divide by the 3 and it would cancel.
Yeah.
All right, so let's distinguish these constant c's from one another. I'll call this c sub 1 and c sub 2. If I combine them, again, we can't assume that they're equal to one another. What's the result of c1 minus c2? Some constant c, right? Yeah. So right there we have our license to not put a plus c on both sides of the equation. All you have to do is put it on the one side. All right. The rest of them go very quickly because they're just fact-based. The first one we talked about already. Antiderivative of cosine is sine x plus c. It'll be heartbreaking. I don't want this to happen, but it always gets somebody. You got to put the plus c every time. You're going to lose credit every single time you don't put it. So train yourselves. And you'll see later on, we'll get into some topics where you get derailed completely if the c isn't there. All right, in the follow-up steps. Antiderivative of sine. Negative cosine x plus c. Antiderivative of secant squared. Tan x plus c. Cosecant squared. Negative cotangent x plus c. Secant tangent. Secant x plus c. Cosecant cotangent. Negative cosecant x plus c. 1 over x. ln x. E to the x. X plus c. And a to the x. Well, it's going to involve an a to the x over, what's it over? Not x plus 1. It feels a lot like the power rule, but it's still exponential. When we took because we want to do the exact opposite of what we would do with a derivative. If I differentiated this, it would be a to the x times ln of a. So the opposite of that. Instead of times ln of a, divide by ln of a. All right. So those are some facts for you. So now you're qualified to tackle the problems on the next page, and that's where we're